Welcome to the lesson on the areas of sector and segment of a circle. At the end of this lesson, you will be able to calculate the area of the sector of a circle, the length of an arc of a sector, and the area of the segment of a circle. Felix is aspiring to be a landscape designer like his father. His father had promised him that during summer break, he could assist him on some of his projects. So here he is, in his father's studio, learning the basics of landscaping design. The project he's working on requires redesigning Mrs. Carter's garden. Mrs. Carter wants her garden to look exactly like the one shown in the picture. It should be circular with a fountain in the middle. Mrs. Carter is a perfectionist, and she likes everything to be perfectly symmetrical. So, Felix's first task is to draw an accurate plan on paper. On analyzing the picture, he finds that the garden is made up of a number of sectors and segments. In order to draw an accurate design, he will need to apply his geometrical skills. Let's see how he manages this task. Felix first draws a circle with the center O. Next, he wants to divide the circle into 6 equal sectors. For this, he draws a chord that passes through the center. Recall that this chord is the diameter of the circle. Next, he draws 2 more diameters. He now has 6 equal sectors. The angles of each sector are 60 degrees. Recall that the part of a circle enclosed by 2 radii and the corresponding arc is called the sector of a circle, and the angle subtended by the corresponding arc of the sector at the center of the circle is called the angle of the sector. Next, Felix draws some more chords as shown. Each chord divides the sector into 2 parts, where one part is a triangle and the other is a segment. Now he has 6 segments. Recall that the part of a circle enclosed by a chord and the corresponding arc is called a segment of the circle. As per Mrs. Carter's requirement, the triangular parts must be covered with grass and the segments with yellow flowers. Felix shows the design to his father, who is very impressed by his neatness and precision. The next task given to Felix is to estimate the quantity of material that will be needed. For this, he will have to calculate the areas of the triangular parts and the segments. Let's see how he does this task. To calculate the area of the segment and the triangular portion, Felix must first calculate the area of the sector. Felix considers one of the sectors, which he marks as OAPB. Here OA and OB are the 2 radii. He labels these as R. APB is the arc that subtends the angle AOB, which he marks as theta. The area of a circle is equal to pi multiplied by the square of the radius, that is, pi r square. Let's consider the circular region to be a sector forming an angle of 360 degrees at the center O. The area of this sector is equal to the area of the circle. This means that the area of a sector of angle 360 degrees is pi times radius square. By this relation, what will be the area of a sector with angle 1 degree? It would be equal to 1 divided by 360 multiplied by pi r square. Similarly, when the angle of the sector is theta degrees, the area of the sector will be equal to theta divided by 360 multiplied by pi r square. This is the formula for the area of a sector, where theta is the angle of the sector and r is the radius of the circle. Now, in the case of the garden, the angle theta is equal to 60 degrees and the radius is equal to 7 feet. Felix substitutes these values in the formula. The area of the sector OAPB is equal to 60 divided by 360 multiplied by pi times 7 square. The value of pi is taken as 22 upon 7. On simplifying these steps, the area of the sector OAPB is equal to 25.67 square feet. There may be situations when the lengths of the arcs of the sectors may also be required. So, how would this be calculated? Remember how the area of a sector was derived from the area of a circle? Using the same logic, the formula for calculating the length of the arcs can be derived. If the angle subtended by the arc is 360 degrees, then the length of the arc of a circle will be equal to the circumference of the circle. Thus, the length of an arc of angle 360 degrees will be equal to 2 pi r, where r is the radius of the circle. Similarly, the length of an arc of an angle 1 degree will be equal to 1 divided by 360 multiplied by 2 pi r. To generalize, if theta is the angle subtended by the arc at the center, then the length of the arc is equal to theta divided by 360 multiplied by 2 pi r. In case of the garden, the angle subtended by the arc is 60 degrees and the radius of the circle is 7 feet. On substituting these values in the formula for the length of an arc, the length of the arc AB is approximately equal to 7.33 feet. Now comes the next part, calculating the area of the segment of a circle. Let's see how Felix calculates this. The area of the segment APB is equal to the area of the sector OAPB minus the area of the triangle OAB. The area of the sector is equal to theta divided by 360 multiplied by pi r square. Recall that the area of a triangle can be calculated as half the product of the base and its corresponding height. Now, the question is, how do you calculate the base and the corresponding height of the triangle? The base and height can be calculated with the help of trigonometric ratios. In triangle AOB, angle AOB is 60 degrees and the side that is equal to the radius of the circle is 7 feet. Now, if a perpendicular is drawn on AB, it will bisect side AB as well as the angle AOB. Recall the theorem. A perpendicular drawn to a chord of a circle from its center divides the chord and the angle subtended by the chord into two equal parts. Thus AM is equal to BM and angle AOM is equal to angle BOM. So angles AOM and BOM are equal to 30 degrees. Now from triangle OMA, OM divided by OA is equal to cos 30 degrees. This implies that OM divided by 7 is equal to the square root of 3 divided by 2. On simplification, we get OM equal to 7 multiplied by the square root of 3 divided by 2. Similarly, AM divided by OA is equal to sin 30 degrees. This implies that AM divided by 7 is equal to 1 upon 2. On simplification, AM is equal to 7 divided by 2. Now base AB is equal to twice AM. This implies that AB is equal to 7 feet. Now the area of triangle OAB is equal to the half of the product of AB and OM. Substitute the values of AB and OM. Let's use the values of the square root of 3 is equal to 1.73. The area of the triangle is nearly equal to 21.19 square feet. Let's substitute the areas of sector OAPB and triangle OAB in equation 1. Therefore, the area of the segment is equal to 4.48 square feet. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. The arc of a circle is a part of the circumference of the circle. The circular region enclosed by two radii and the corresponding arc of a circle is called the sector of a circle. The circular region enclosed between a chord and the corresponding arc is called the segment of a circle. The angle of a sector is the angle subtended by the arc of the sector. The circumference of a circle is equal to 2 pi r, where r is the radius of the circle. The area of a circle is equal to pi r square. The length of the arc of a sector of angle theta is theta divided by 360 multiplied by 2 pi r. The area of a sector of angle theta is theta divided by 360 multiplied by pi r square. The area of a segment is the area of the corresponding sector minus the area of the corresponding triangle. Hope you enjoyed this learning experience. Welcome to the lesson on areas of combination of plane figures. At the end of the lesson, you will be able to determine the area of combination of plane figures. Sam's father Joe is a carpenter. In his free time, Sam helps his father with his carpentry. Joe makes wooden furniture. He uses veneer of different colors to design the surface. Last Sunday, Joe helped his father to make a table. Its top had a design that looked like a circle inscribed in a square. As you can see, the circular region is in blue, and the rest of it is in white. Joe now wants to make a table with a different design, and he would like Sam to help him. He shows him the design he has created and asks Sam to cut the blue veneer. Here, Sam can see that the blue portion of the design is not a standard shape and wonders how he will be able to cut such a shape. Joe gives Sam two separate pieces of veneer, one square and one circular. Sam thinks for a while. Then he gets an idea. He places the circular veneer in the center of the square and draws an outline of the circle. Then he places the circular veneer on one corner of the square veneer and draws an outline of the quadrant of the circle. Similarly, he marks quadrants on the rest of the corners. Finally, he cuts the marked portions of the blue veneer. Voila! There it is! He found a technique to remove the unwanted areas from the veneer to get the required design. Here's a recap of what Sam did. He took a blue square veneer, marked a circular shape in the center, and 4 quadrants on the corners. Then he cut the marked portions. If Sam wants to find the area of this shape, he simply has to subtract the area of the cut portions from the total area. In this case, the cut portions are a circle and 4 quadrants of a circle. That is, the area of the square minus the area of the circle minus the area of the 4 quadrants. Now, we will see how Sam and his father plan to make a door for the restaurant. The design of the door looks like this. It is 2 meters in height, 2 meters in width, consists of 2 wings, and the outer shape resembles a square. They would like to use glass and wood to make this door, where the glass occupies the semicircular shape on each wing of the door. Again, the combination of standard shapes, square and circle, is involved in the design of the door. Here they will have to cut 2 semicircles from the square that has a side of 2 meters. Now, they want to order the glass for the door. For this, they have to calculate the area of the glass required. You can observe that the glass portions of the door are semicircular in shape. Therefore, the area of the semicircle is the area of the glass. The diameter of the semicircle is the height of the door, which is equal to 2 meters. This implies that the radius is 1 meter. Recall that the area of the semicircle is half pi r square. Therefore, the area is equal to 1.57 square meters. Therefore, the area of the glass required to make the door is 2 times 1.57 square meters, that is 3.14 square meters. Then, what is the required area of the wood? The wood required is equal to the total area of the door minus the area of the glass. The door resembles a square, where each side equals 2 meters. Therefore, the total area of the door is 4 square meters. So the area of the wood required is the area of the door minus the area of the glass, which is equal to 0.86 square meters. This means that Joe needs to buy nearly 1 square meter of wood. This is the advantage of designing on paper before building anything. So far, we have seen how Joe and Sam worked on furniture. Now, we will see a few more examples of how the areas of non-standard figures are calculated. The examples we will see here involve basic geometric figures such as circles, squares, triangles, rectangles, etc. Look at the first example. Here we have to calculate the area of the figure which has a non-standard form. Let's try to analyze the figure. We can visualize the figure as 3 parts. It is a combination of a rectangle and 2 semicircles. Therefore, the area of the figure is the sum of the areas of a rectangle and the 2 semicircles. Let's see another example to understand the method better. Here's a figure composed of 2 concentric circles. To obtain the area of the shaded region, let's follow the procedure. Now, the area of the shade region is equal to Here's another example. This figure is a combination of a circle and a square. Here we have to find the area of the shaded region. Let's analyze the figure. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. In this lesson, we have tried to understand that a non-standard shape is composed of different standard shapes. We have also seen how to calculate the area of the non-standard shapes. Hope you enjoyed this learning experience.